In this lesson, we're going to look at how we can design a current source using a switch mode converter, specifically a buck converter, and specifically a buck converter that operates in the discontinuous conduction mode. Let's begin by drawing an ideal circuit. Maybe I'll first draw an actual simplified buck circuit, and then we'll go to the ideal one, which is the one that we will use to describe the principle of operation and some of the salient equations that describe the operating point of a converter. Okay, so we would have some kind of a voltage source, VG, generator, some input capacitor, then some power transistor. It could be either polarity and channel in this case. So this is drain and source, and then a rectifying diode. If this is a low voltage application, then we probably would use a Schottky diode because it has a lower forward voltage, but those go up only to about 200 volts. And so we have our inductor. This is a power inductor that is designed to handle high frequency, meaning 100 kilohertz, somewhere 1/10 to 10 times 100 kilohertz frequency range, and it handles DC current. Then we'd have some output filter capacitor. I'm drawing just one capacitor, but typically there would be a number of capacitors. Electrolytic capacitor for providing significant energy storage, bulk capacitance, but then also some smaller ceramic, perhaps ceramic capacitors in parallel, which have lower series inductance and behave as a capacitor up to much higher frequencies, where an electrolytic capacitor will cease behaving as a capacitor and will start to act more like an inductor because of the effective parasitic ESL, effective series inductance, that is inherent to all capacitors, but is certainly going to be much higher for electrolytic capacitors. Okay, and then we would have a load. Now the load could be a resistor, it could be a current source. I'll go ahead and draw it as a resistor for a moment. All right, and we have a voltage V out, and we'd have a current IL and an average current IO and a current IN or II, and this current here, oh wait, maybe I should call it, that'd be I switch, and II, and then ID, and I could say ICO. Okay, so that's what a real, well, and then we need to provide some kind of a gate drive circuit. I will just draw it in a generic form where we'd have some kind of a PWM controller, grounded, be some supply VDD, and it would provide some kind of a periodic pulse, which typically is going to be constant frequency, but it would have variable on time. The on time would be T on equal to TS times the duty cycle D. And the input to this PWM controller would typically include VO and then some V reference. And there might be, depending on the type of controller, there might be information about IL or I switch or even I diode, depending on the type of controller. Okay, and essentially in that PWM controller, if you're trying to regulate the output voltage, which is kind of how I've drawn it here, that we're trying to control the output and make the output follow some reference or comply with some voltage reference, then the duty cycle on the switch will adjust itself or be adjusted so as to drive VO to VREF, much like the throttle on your car would be adjusted to maintain some speed that your cruise control would be demanding. And to help actually achieve that in a more controlled, better behaved fashion, a lot of times information about the actual current in the inductor is fed back, and there's an inner feedback loop that controls the current first, and then that feedback loop is fed a reference current. That reference current is generated from an outside or an outer feedback loop that involves Vout and Vref. You can imagine that without monitoring the current and just looking at the output voltage and controlling the duty cycle, what we can end up with is a underdamped response of the system, because the inductor L1 and the output capacitance CO are a second order system that theoretically could oscillate. And so anyway, having current feedback helps to avoid that problem. So this is a more realistic schematic of what you might have for an actual buck converter, but in order to design or explain the principle of operation, we're going to redraw this much more ideally. Okay, so we're going to start with the voltage source VG, or maybe I'll just call it VN. We have a switch S, we have an ideal diode D, we have our inductor L, and then for the output, what we're going to actually draw is Vout. Now, of course, there is no physical output voltage. That would, I mean, you could come close to that if you were, say, charging a battery. That voltage is not going to change very quickly, but even if it's a capacitor CO and a load resistor, R load, the time constant of that R load times CO is going to be much, much, much greater than the switching period of this converter. And if it wasn't so, then you'd have a lot of voltage ripple on the output, and that's one of the requirements of a converter or power supply, is that you have a DC output voltage that's not going to have a lot of ripple. So the time constant, R load times C out, is going to be much, much greater than the switching period, TS, which we have over here, switching period. And so because of that, the voltage across CO is not going to change noticeably within one switching period. It'll change over many periods, but not over one switching period. And we're going to now study how this circuit works over a switching period. So we can say here that this VO, the average value will equal, well, if there's a load R load, it'll be R load times whatever the average output current is. Okay, I'll put a bar over there. For the moment, we're going to just assume a VO and study the circuit just like that. So let me label some voltages, some current. So we have V switch, across the voltage across the switch. We have VD, which, notice this is equal to minus V forward, which typically has an opposite polarity, right? So, but I'm going to label it VD in this manner. And then we have VL, and we have IL. Notice that IL, in the simple form, IL and IO are the same thing. But we do notice that ultimately in a real circuit, the IO is really the current that's flowing out of the buck converter that includes a large filtering capacitor and is flowing to the load. We see that right here. So there are several circuit modes. Oh, I should first define a couple notes here. Note D is ideal. S is also ideal, meaning 0 ohms on, 0 ohms, infinite ohms on, off, right? D is ideal in that it is 0 volts. they both switch in 0 time, no switching loss. L has 0 ohms of resistance. Okay, so note there are no lossy elements. Now, of course, that's not realistic, but we can still determine the basic principle of operation, and then we can add in some lossy elements to our analysis later. Okay, we also need to define the switch control. So we will turn on for a period and then off for a period. And the way I'm going to define this is the period is actually TS, but I'm going to plot this as T over TS, so it's going to be normalized. I don't know why I'm going to do this, but I think it'll be beneficial, at least initially here, as one view of how to look at these waveforms. So now I can just define duty cycle D, okay, and then 1 minus D, and the period is 1, right? Of course, the period is actually TS. So the transistor is on here, the transistor is off here, it's on here, and so forth. Okay, so that is our ideal circuit. Now we're going to look at the circuit modes. There are 3 modes, 3 circuit modes. First case is, well, in principle, let's think about it. There's a diode and there's a switch, S and D. S can be on, S can be off, D can be on, D can be off. There's 4 permutations there, right? But we can immediately eliminate S and the diode being on, because if S is on, then we're applying V in across the diode, and V forward, VF would be minus V in, so the diode would be off. So there is no case where both are on. So therefore we're going to have S on, D off. We could have S off, D off, and then we could have S off, D on. So let's look at those. So circuit mode 1, we'll say S is on, D is off. I won't even bother drawing the switch because it's a dead short. It's an ideal switch. Okay. Circuit mode 2 is going to be when S is off and D is on. In this case, there is no path through the switch. However, the diode is on. I'll go ahead and dot that in. So note that the current is going through the diode, whereas before the current was going through the switch. The voltage across the switch at this point we would define as V switch, and this is V in, VO, and then the third circuit mode is when S and D are off. And when that is the case, there's no path for the current. So IL is 0, and I switch is 0, and I diode is 0. Okay, so let's describe what happens in each of these circuit modes. When the switch is on, let's say the switch will turn on at time t0, and it'll turn off at time t1, where t1 is going to be equal to t0 plus D duty cycle times TS, right? And this would be, we could define this as the on time of the switch. During this time, VL is equal to Vn minus VO. Since IL is equal to L, or VL is equal to L di dt, we can write that DIL dt is equal to VL over L, or VN minus VO over L. I'm just going to call this VI. Okay. So it has a fixed slope. It's positive, so this is greater than 0. So the current is going to be rising, IL. And it's going to have a slope of VI minus VO over L. It's going to rise for a duration of T on, which is equal to D times TS. The current will go from IL0 to IL1. And what we can write is that IL1, which is really IL at T1, right, is equal to IL0 plus, we can say delta IL, where delta IL is going to be equal to VI minus VO all divided by L times D times TS. That's what happens during circuit mode M1. So if we stay in that circuit mode, the current just keeps increasing, and it'll keep doing that until we turn off the switch, at least in this ideal circuit. The other thing we can note is that V diode is equal to V in during this time. Okay? And of course, V switch is equal to 0 during this time. ID is equal to 0 as well. And I guess we should write that I switch is equal to IL during this time. Okay, circuit mode M2 occurs when at time T1 we turn off the switch. We go back and look at our circuit. If we have current flowing initially out through the inductor to V out, when we turn that switch off, imagine that there's a little bit of capacitance across that switch. The inductive nature of the inductor will cause the current to continue flowing. Actually, what will happen is the current will not change until VL changes, and VL cannot change until the voltage across the switch rises. But for it to rise, imagine if there's some capacitance there, it's going to take a little bit of time, albeit maybe nanoseconds, for that voltage to rise. And it will rise very quickly, and it will rise up to a voltage of Vn. And you might say, well, why does it go all the way to Vn? Well, there's enough, the assumption is there's enough energy in the inductor that it would take tremendous amount of voltage across that tiny little capacitance of the switch to store all that energy that was initially in the inductor. So the switch voltage will rise to Vn, at which point the voltage across Vd will be 0. Note that V switch plus Vd is always equal to Vn. Okay, so as the switch voltage rises, the diode voltage goes down. Eventually the diode voltage will actually reach 0 and go slightly negative, but in this ideal case, once the diode reaches 0, the diode will turn on, and the current will stop trying to flow through the switch that's now opened, and the current will flow through the diode, and that's how we get to circuit mode M2. So circuit mode M2 starts at T1, which is equal to T0 plus dTs, and it goes to T2, where T2, we have yet to determine what T2 is, so I'll leave that be for now. Now VL during this time, is VL, is going to be equal to minus VO. Previously it was VI minus VO, but now that VI is disconnected and instead we have a shorted diode, it's just 0 minus VO. 0 minus VO, or I could write, it's really, if this is VD, we could say that it's VD minus VO, which in this case is minus VO. The time rate of change of the inductor is now going to be negative. It'll be equal to minus VD minus VO over L, which is just minus VO over L. So the inductor current is going to come down at a slope of minus VO over VL. Okay, now if this is 0 here, then actually let's do this. Let's define, okay, this is going to be TS, we'll call this TS times D2, duty cycle 2. The delta IL during this time will be equal to minus VO over L times TS times D2. And we can say VD is equal to 0 and ID is equal to IL, and V switch is equal to Vn, and I switch is equal to 0. Okay, so lastly we have circuit mode C3, and let's work through that, and then we'll put this together into something that's coherent. Okay, so we don't know yet if IL2, that is the current at this point here, IL2, this would be IL1. If IL2 is equal to 0, okay, then we would have from T2 to T3, we'd be in this circuit mode here, where T3 is equal to T0 plus the switching period. All right. Now we'll see that if we operate in one mode called continuous conduction mode, we only go between circuit mode M1, CM1, and CM2. But if we leave the switch off long enough such that the inductor current decreases to all the way back down to 0, where IL2 now is 0, and we linger longer with the switch off, then we'd enter into circuit mode 3, and we'd call that discontinuous conduction mode. So this only appears in discontinuous conduction mode. And here we have V switch is equal to, well, what we start out with, we'd say I switch equals I diode equals IL equals 0. Okay, and the question of what V switch is equal to, we're not sure, and VD, not sure. But if you treat these exactly as ideal, no, what am I saying? Ignore that. Okay, because we can say that VL is equal to 0 because DIL dt is equal to 0, right? So there's no voltage across across the inductor. So therefore, this point here, if we call that V, well, that would be V switch. V switch is equal to VO, and VD, not V switch, that is V diode. Okay, V diode is equal to VO, and V switch is equal to Vn minus VO. So nothing's really happening in that mode. Okay, so those are the 3 circuit modes. So now let's put this together. Let's assume we're going to look at both modes, where first we'll look at continuous conduction mode, CCM, and then we'll look at discontinuous continuous. Okay, so what we have is the switch turns on, and then it turns off, turns on, turns off, so forth. So this is the switch, and it is on for DTS, It is off for 1 minus dTs. It has a period of Ts. And the current will rise. This is IL. Current will rise during the on time of the switch, and it will fall during the off time. The slope will be Vn minus Vo over L, and then it will be minus Vo over L. We can note the peak-to-peak current, or delta IL. Say I peak to peak. And okay, so zero current is down here. So what happens in this case is that when we turn the switch off and the current falls, the current does not actually fall all the way to zero before we turn the switch back on again. So we have what we call continuous conduction mode, because the inductor is continuously conducting the entire time. Let's label some time periods. We're going to be operating in circuit mode 1, and then circuit mode 2. Circuit mode 2. Okay, the voltage on the switch would be equal to 0 when the switch is on. When the switch is off, it's going to be Vn. And okay, and then if we draw the diode current, or diode voltage, the diode voltage will be equal to Vn. This is going to be V diode. So they just complement each other. Okay, so the maximum voltage stress on these devices, the switch and the transistor and the diode, is going to be ideally just Vn. Okay, so let's write down some relationships here. We've already found that delta IL in circuit mode 1 is equal to Vn minus Vo over L times D times Ts. Right here. Right. And during the off time, it's minus Vo over L times Ts times D2. Delta IL CM2 is minus Vo over L times D2 times Ts. But in this case, D2 is actually 1 minus D, because we're in continuous conduction mode. In steady state, the current at the end of the period right here needs to be equal to the current at the beginning of the period. And so we can write that IL at T2 must be equal to IL at T1. And this means that IL of T1 plus delta IL CM1 plus delta IL CM2, this right here, is actually ILT2, right? That must equal ILT1. And so when we combine these two, we can write that delta ILCM1 must be equal to minus delta ILCM2. In other words, by however much the current rises here, it must fall by the same amount during the off time, so that we actually end up at the same starting current on the next cycle, and that's what defines steady state. So using these two expressions, we can, and noting that we have Ts that's common to both of them and L, we can write that Vi minus Vo, of course I'll go ahead and write it over L, dTs is equal to Vo, not minus Vo, because we have a minus delta IL CM2, times D2, which is, we've already noted, is 1 minus D times TS. The TS's cross out, the L's cross out. And we arrive at VI minus VO times D is equal to 1 minus D times VO. We collect the terms, VO particular, and we have VI times D is equal to 1 minus D VO plus D VO, and that end up canceling these, so we end up with just VO. And this leads to our very simple expression that the output voltage VO must be equal to VI times D, or, yeah, I guess I'll leave it like that. Okay, this is in steady state, and this is continuous conduction mode. Notice that in this case, the relationship between the output and the input voltage in the duty cycle are independent of the current, right? So in the end, the circuit we're going to build is actually the circuit on the right here, and it does have an output current I/O, and we're going to set an R load. And what this is saying is that in continuous conduction mode, if we have ideal components, not meaning, in this case, not meaning that we have to have a voltage source at the output. It's fine to have an output capacitor CO and an output resistor R load. But when we mean by ideal, we mean the switch has 0 on resistance, the diode has 0 voltage drop, the inductor has no winding resistance, there's no switching loss. If that's the case, and a lot of times we can get pretty close to that, at least within some range of operation, then we can have a converter where the output voltage does not change even as the output resistance, our load, changes, and we demand more current or less current. Now, in any real converter, there will be some dependency, and that's why you need a feedback controller that measures the output voltage and adjusts the duty cycle. But a lot of times it doesn't have to adjust it very much. Now, there's a lot of additional things that we can calculate related to this operation mode, particularly some of the stresses on the components, because you need to calculate stresses and losses. And so maybe I'll spend a couple minutes here. We'll work through some of the major ones. Okay, so let me make the note here. Note: independent of I load or R load. Okay. Okay, so let's look at the switch. Okay, so V switch max, we already saw is just Vn. Okay. I switch peak. Okay, the peak. Now maybe we'll start with I switch average. I didn't draw the current here, but for the switch, but the switch current is going to be, here's the switch voltage. So the switch current would look like this. Okay. And the diode current is going to look like, it'll be 0, and it'll jump up. Oops. Draw it over here. It'll be 0, then it'll jump up, and it'll fall. It'll conduct during the falling time, and it'll be zeroed again. So the average switch current, it looks like this. Well, should be able to convince yourself that it's going to be the average output current, IL, times the duty cycle. Okay, and this is going to be equal to the average output current times the duty cycle. Recall that even though we've treated this in this ideal circuit with just a voltage source here, in the end that voltage source is made up of a capacitor and a resistor, a capacitor, and a current sink. And so the average current going into this capacitor here has to be 0. So that means that IL on average has to be equal to IO on average. Okay, so we can write it's the average output current times D. We can also then ask, well, what is the RMS? I switch RMS. Well, that one we can approximate as, we can approach it two ways. The first way is we assume that we have a square current like this that has a value IL or IO during this period of time, and it has this conduction of D and 1 minus D. This would be where we'd be plotting T over TS, right? Normalized time. So this is a simple RMS calculation. It's the amplitude times the square root of the duty cycle. A more accurate one would be if you include the triangular portion of it. And that one, I'm going to skip that right now because that's not critical for this. But you can come up with a more accurate calculation for the RMS current. This actually then leads to the power in the switch, like conduction loss, right, is going to be I switch RMS squared times RDS on, right? So that's why you want to know the RMS. You also want to know the switch peak current, right? Because that would tell you, for instance, if you were dealing with really high currents, maybe there's some condition where you have to be careful whether or not the peak current is more than what your switch can handle. Usually that's not the case. But the peak current here would be IL or IO, the average output current, plus 1/2 of the inductor peak-to-peak current. And the peak-to-peak current, we can find several ways. It's the VI minus VO over L times D times TS. It's also equal to VO over L times 1 minus D times TS. So you can use either one of those and you can calculate what the peak current is. Okay, we also should look at the diode. Okay, diode. The diode max voltage is going to be equal to Vn, just like for the switch. And here the average diode current, if we note that the diode current is this green here, right, then it will have an average current, because it looks like this. And this here is IO. And the period, or this period, is 1 minus D, and this is D, right? We're plotting T over TS here. So the average is just simply IO times 1 minus D, just like the switch average current was IO times D. And in the case of the diode, we're more interested in the average current than we are in the RMS current. Okay, and what we would do is if you have a diode curve that shows I forward and V forward, and it does this kind of a thing, what you want to do is you want to pick out, you want to look at the IO case. You don't want to look up on this curve the average diode current. You want to look at the average current during the time that you're conducting, when the diode is conducting, and that average current is going to be IO. So you want to spot IO on your curve, and then you'll come down and you'll find VF, if you will, and now the average P diode conduction will be equal to, or approximately equal to, V forward O times IO times 1 minus D, because you're losing this much power for a percentage of 1 minus D. Okay, I think that's enough for, well, what else should we do? You're also going to want to know the inductor. Okay, inductor, because, yeah, you need to know IL, the average, which we know that's just IO, and then you're going to need to know IL peak. That's important. That will be the same thing as the I switch peak. It's right, this is also equal to IL peak. So IL peak, this is going to be your IO plus your 1/2 delta IL peak to peak, which you can calculate from here. Okay, and why is that important? When you pick your inductor, there's a couple things you want to be careful of. For your inductor, you want to look at I squared R heating. So this will typically have there'll be a I DC limit. Okay, and that's not because the core is going to saturate or it's going to stop acting like an inductor, just because there's too much I squared R loss. If they specify it as IDC, specifically, technically you should be using the RMS current of the inductor, but if your current is largely DC with a small ripple, okay, then in this case IDC is approximately IRMS, or vice versa. IRMS is about IDC, and so oftentimes in the data sheet you'll just see a specification for the IDC limit, and you use that for your heating, right? You can use the DC resistance that's specified for the inductor times your DC current squared, and that can be an estimate of your conduction losses in your inductor. Now the other thing you want to look at is the peak current, or what often is going to be called the ISAT, saturation. And this will be specified in different manners, but a lot of times this is maybe defined at 20% loss of initial L. And what's happening is, as you push more current through the coil, the magnetomotive force H becomes stronger and stronger, and the resulting B that comes from H, and H comes from Ni is equal to H dot dl. Okay, the more, and this is N is the turns, the more current you push through your coil, the more H is generated, and the magnetomotive force H then drives, kind of like a potential, if you will, that drives a current. Think of B as being a current, and mu, the permeability of the core, is like the conductivity of the material. But unfortunately, mu eventually drops off, so it may be constant for a time, but as current goes up, eventually it drops off. And so incrementally, you get this smaller and smaller incremental change in B, and therefore phi, in the presence of the same delta I, and that translates ultimately in having a reduced inductance. And so eventually, very quickly actually, in most, well, it depends on the inductor design, the core design, but the inductance will fall rapidly away from its initial value. So that's why you want to calculate the peak current, because you want to compare that to the saturation current. Okay, well, that's plenty of information on component stresses. I think now we're ready to look at the discontinuous conduction mode, and actually the discontinuous conduction mode is the mode that I'm going to recommend for this current source. Now, I started out by saying this is designing a DCM Buck converter current source, but we haven't talked anything about a current source yet. Actually, all I've talked about is a voltage source, right? We've talked about actually trying to program an output voltage. But in our application, or the one that's leading me to do this video, is where we need a converter to provide a constant current to a load. And we're going to find that, or I'm going to propose using the discontinuous conduction mode, because it is a very simple way to produce a constant current. Okay, so in the discontinuous conduction mode, maybe I can copy some waveforms here. Okay, so in the discontinuous conduction mode, the current starts at 0, and it still rises with the same VI minus VO over L, same slope as before. The difference is it falls at a rate, still minus V over L, but either VO is higher and so it falls at a greater rate, or we have extended our period such that the inductor returns to 0 before we're ready to turn our switch on. So this leads to the third circuit mode. We'll have CM2, and then we'll have CM3 right here. And the current during this time is going to be flat. And then it'll go up again, come down again to 0, start off once again. Okay, Vin will be, V switch will be 0. It'll come up to Vin, and then let me redraw this. When we get to CM3, actually it's going to drop to VO, which is kind of interesting, and we'll talk about that in a little bit. Okay, and the diode voltage will be 0, will be Vn, then it will drop to 0, and it will also come up to VO during CM3. Nope, it's not. What did I say? It will come up to a smaller voltage here, yes. Okay. V diode, V switch. Fortunately, the diode and voltage and the switch voltages are not the critical signals that you have to understand for understanding the overall circuit operation. Okay, so in this case, we have IL of T0 is equal to 0. Right? IL of T1 is now equal to 0 plus delta IL peak to peak, which is simply our VI minus VO over L times D times TS. So we can write, therefore, that IL peak, the peak current, which is also equal to IL of T1, which is also the delta IL peak to peak. I guess these are all the same. Can say IL peak is equal to Vn minus VO over L times D times TS, or we could also write it as Vn minus VO over L Fs. I haven't used Fs yet, but Fs is the switching frequency. So we know what the peak current is, and we need to know, okay, I need to clear up the time 2 is no longer, we need to redefine time 2. Okay, and time 3 is the one that's equal to time T0 plus Ts. So what is time T2? Well, we note that delta IL CM1, recall that we had written an expression for that up here. Delta IM, where can I find it? Yeah, right here. That's delta IM CM1, if you will. Delta IL CM2. These must be equal to each other in magnitude. okay? Because, again, it starts at 0, it's going to end up at 0. So we can write that delta IL CM1 is equal to delta IL CM2. VI minus VO over L times DTS must be equal to VO over L times times D, I'm going to call it D2, this period here. It's the other thing that's not right on here. Well, no, that is correct. That is correct. It is. This is 1 minus D, but it's not very helpful. What we really want to know, this time here, I'm going to call D2. Okay, the amount of time for the discharge time. The L's cross out. TS's cross out. And we are left with VI minus VO times D is equal to VO times D2. Or D2 is equal to VI minus VO over VO times D. This leads to T, call it DT discharge, which is equal to T2 minus T1, is going to be equal to VI minus VO over VO times DTS. Okay, so now we can solve for some useful things. So we know that we charge for a period DTS and we discharge for a period D2TS, and we're 0 for a period of time. So this has a duration of DTS. This has a duration of D2TS, which we have found is equal to VI minus VO over VO times D times TS. Okay, and that means that the sum of these two, D plus D2, which I'm going to define as DC, conduction duty, is equal to VI over VO times D. So that's an important result here. D conduction is VI over VO times D. I'm just double checking today. Is that right? You put over a common denominator VO and we would get, yeah, the VO would cancel. Okay. So from this, knowing this is IL of T here, we can arrive at IL average. The average current, where the peak here, IL peak, we have already found, we can write the average as being 1/2 times IL peak times, now we need the duty cycle, the conduction duty cycle. And this is equal to 1/2. What is IL peak? We have found IL peak. Did I not put a box around it right here? Okay. 1/2 VI minus VO over L Fs times D, and now that is times DC, which is VI over VO times D. So IL average is equal to, let's see, 1/2 VI minus VO times VI divided by, let me write it this way, VI minus VO divided by 2 LFS times VI over VO times D squared. Okay, so this is an interesting result because what we find now is that for the discontinuous conduction mode, controlling the duty cycle doesn't directly control the output voltage or force the output voltage. Instead, it programs a particular average output current. Notice that this output current is a function of VI and a function of VO, so if those voltages do change, then clearly the current is going to change as well. However, if you are able to measure VI and you measure VO and you know the value of inductance that you're working with, then you can program the average output current. Remember that IO on average is IL. You can program the average output current by setting the duty cycle, and this is one of the merits of being able to, of using discontinuous conduction mode, is that we don't need to specifically measure the current and then feed that back in some loop to regulate it. Instead, we simply need to measure the input voltage, the output voltage, make sure that we know the inductance and that we operate at a known frequency, and we can deterministically program the output current by simply controlling the duty cycle. Now, if we wanted to consider, what kind of output voltage would we actually have if we return to our original circuit and recognize that, in fact, we do have a load here, our load, then we would have to take this result and say, let me write it this way, if output consists our load, then in steady state we would have VO is equal to R load times IL load, which is equal to R load times VI minus VO, all of the same expression that we had previously. And we note that this is a quadratic in VO, right? We'll have VO squared equal to 1 over 2 LFS times VI squared D squared minus VI DI squared over 2 LFS times VO, right? And this is you'd have to use quadratic formula to solve, right? I won't do that now. That's what you need to do to calculate the output voltage if your load is actually a resistor. However, if your output is much more closer to a voltage source, such as if you're charging a battery, then you don't have to apply that condition. You can simply say, I'm going to monitor what my output voltage is as my battery charges over time. Then I'm going to monitor that, and I will adjust the duty cycle as necessary to maintain the charging current that I want.